All right, Volodya, go ahead.
Okay. Hello, everybody. I have a pleasure to present our speaker of today, Oleg Lisovyy from Tours, my close neighbor, and he will speak about something very interesting, I hope. Please, Oleg.
Thank you very much, and thanks for everyone for coming. So, can you see my screen?
I think yes. Okay.
Yeah.
Yes, it's fine.
Okay. Now I have to make some arrangements of windows. Actually, I have lost Zoom window by sharing the screen. So just a second. Okay, well, anyhow, since you can see...
we see you and we see your whiteboard, so it's fine.
Okay, yeah.
It is rather thin board.
So the main theme of my lectures will be the reconstruction of linear ODEs from the monodromy. And as we will see, different incarnation of this problem lead to several interesting classes of special functions. So what I'm going to explain is how these functions are defined. Then we will discuss some methods of their computation.
Oleg, just a comment. We see your right shoulder, and that's all.
Yeah, this is because I have a strange arrangement of screens. So I would actually like to switch off the video from my side, but I don't know how to do it because I only see many windows of participants.
Well, because well, then you have to change the view from the gallery to the speaker view. In this upper right corner view, do you have it?
Well, the gallery I do have, but I don't know how to change to the speaker.
But maybe if you slightly turn your screen towards you.
Yeah, is it better?
If you click on view, you must...
Yeah, that's nice, I guess. We will see you and your writing. So
no, with us there is no problem. If everyone will just keep muted, then we'll see only Oleg and your writing. So that's it.
Okay, so right. So what I said is that so I want to define these special functions that arise in the inverse monodromy problems. I want to discuss methods of the computation and finally some relations between them. So these lectures are supposed to be rather elementary, so hopefully only very low level background is needed to follow. Yeah, and here is an outline. So first we are going to speak about this class of special functions which are called accessory parameters in the differential equations of Hoyne type. So basically a second order linear scalar ODEs. And so the relevant function is essentially something like the energy in the Schrödinger equation with a particular, with a suitable polynomial or rational potential. So I will focus on the example of Mathieu equation, which is just this Schrödinger equation with cosine potential. And for it, we will discuss the direct and inverse monodromy problem, and also how this can be solved using Hill's determinant and continued fractions. So this is all very classical 19th century mathematics. Then we will continue with linear systems. And in this case, what I want to explain is how the inverse monodromy problem for the linear systems, how the solution of this problem is equivalent to solving Painlevé equations, at least in the simplest cases, for simplest classes of linear systems. Then the third part will be devoted to solution of this inverse monodromy problem. Namely, we are going to obtain two types of explicit representations for Painlevé functions. So one of them will involve Fredholm determinants, and the other one will involve series. So, so using these two representations, basically it gives us the solution of the second point. And then in the fourth part, I will introduce the third class of special functions that we are going to be interested in. So this arises in the representation theory of the Virasoro algebra, and they are called Virasoro conformal blocks. So I'm going to explain that the first class of special functions, so these accessory parameters, are related to what is called quasiclassical Virasoro conformal blocks. So this corresponds to the Virasoro central charge, which goes to infinity, and Painlevé functions, so the solutions of inverse monodromy problem for the linear systems, they will be related to C equal to 1 conformal block. So this is what I wanted to discuss in the first part, but of course everything will depend on how fast it will go. And in the second part, I am going to use the relation, the classical relation between Painlevé functions and accessory parameters in order to prove certain identities involving C equal to 1 and C equal to infinity conformal blocks. So these identities have the meaning of the so-called blow-up equations in conformal field theory. Okay, and of course there are many open questions that I will try to emphasize along the talk. Fine. So let me start with this Mathieu equation. So I rewrite it once again. So we have this 2 lambda times cosine 2x. This is the potential, the wave function, and the energy. So as I said, this is a Schrödinger equation with periodic potential. So the Hamiltonian, which is here, it commutes with the translation operator, which sends x to x plus pi. And then, according to the general ideology, so this two operators, H and translation operators, they can be diagonalized simultaneously. and which is why we can look for solutions of this Mathieu equation in the Floquet form. So we say that psi of x is equal to I mu x and a sum over integers an exponential of 2in x. So this is the Floquet ansatz. And so the goal here is the following. So we have two questions. So question one is given the energy, find the quasi-momentum nu, so this parameter which appears here. Question two, given nu, we want to find the energy. So I will refer to this question as the direct monodromy problem, and to question two as the inverse monodromy problem for Mathieu equation. So now why I'm talking about monodromy? Well, because if we make in this equation a simple change of variables, if we go from this x to a variable z, which is exponential of 2ix, then we can rewrite our Schrödinger equation in the form psi, let's say twiddle 2 prime of z plus a potential, which is now a rational function of z. So this v of z has the form, well, roughly speaking, this is something like lambda over z cubed minus e over z squared plus lambda over z. So you see that the points z equal to 0 and z equal to infinity are the singular points for this equation. And going around any of them will produce a monodromy. The monodromy which is sitting in this factor here. So this is basically something like z to the power nu over 2. So when we make this Floquet substitution, basically we choose the basis of solutions in such a way that they diagonalize the operator of analytic continuation around, let's say, the singular point z equal to 0 of this equation. Okay. So nu plays the role of monodromy, and E is a parameter of the equation which we want to relate to nu. Now, how can this be done? Well, this is actually very easy in a way. So we just have to plug this Floquet ansatz into the equation so that it becomes a difference equation for the coefficients an. So when we differentiate 2 times the exponential, we get something like nu plus 2n squared. Then we have minus e times an, and the cosine term produces something like lambda an minus 1 plus lambda an plus 1. So this should be equal to 0. Okay. So instead of a linear ODE, we get a linear difference equation. Now, this is homogeneous, and therefore a non-trivial solution exists only if the determinant of the corresponding matrix producing this linear system is equal to 0. So let us try to write this determinant. So we have this nu plus 0 squared minus e, nu plus 2 squared minus e. So these are the diagonal terms. And so this continues up to infinity. And we also have these lambdas here, 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 and here. So we have this huge doubly infinite matrix, and for the existence of a non-trivial solution of this equation, we would like to have the determinant of this matrix equal to 0. Right? But the determinant is ill-defined because clearly, at least the diagonal terms, they tend to infinity when this n increases. So to make the determinant convergent, one possible trick is to divide every line by the by an appropriate scalar factor. For example, we can divide by 0 squared minus e, here 0 squared minus e, 0 squared minus e. Then here we divide by 2 squared minus e, 2 squared minus e, and so on. So in this way, we now get a convergent determinant. So let's call this determinant delta of mu. I will perhaps erase the 0 for now and put here delta of mu. And so the existence of a non-trivial solution is equivalent to saying that well, we want this delta of mu to be equal to 0. So this is, by the way, what is called Hill's determinant. And what is remarkable is that we can actually separate completely the dependence of this determinant of on monodromy. So here is a formula, a magic formula, which was discovered by Hill. So Hill's formula. So this delta of mu is equal to delta of 0 minus sine squared of p nu over sine squared of p square root of the energy divided by 2. Okay. And what is remarkable is that this formula actually holds not only for Mathieu equation, but for any periodic potential. Any periodic potential. So no integrability here. And now you see that what do we get in this way? So when we want this Hill's determinant to be 0, then we can express from this equation here, we can express sine squared of p nu, which is our monodromy parameter. We can express this as sine squared of P square root of energy over 2, and then, well, some huge determinant, infinite determinant, which I'm not going to rewrite it, but the point is that it depends only on the energy, right? So, so we get these identities on the diagonal and some elements out of the diagonal, but no dependence on nu. So we have nu as a function of E. And so this is the solution, a formal solution to the direct monodromy problem for Mathieu equation. Now, what about the inverse monodromy problem? So in the inverse monodromy problem, instead of having this nu as a function of E, we would like to have E as a function of nu. And in principle, we can solve for E perturbatively, provided that the parameter lambda here, or these lambdas which stand outside the main diagonal. So if this parameter is small, then, well, we can perturbatively compute the determinant at any desired order in lambda. And this basically allows us to solve the inverse problem. However, there is a much more efficient way to do it, which I am about to discuss now. So we suppose that the parameter lambda, so this parameter of the potential, is sufficiently small. And well, let me rewrite once again the difference equation that we had. So we had nu plus 2n squared minus E times an plus lambda n minus 1 plus n plus 1 equal to 0. Now, in this difference equation, so there is a familiar procedure, like when you have a second order differential equation which is linear, you can easily go from it to a first order nonlinear Riccati equation. So this is what we are going to do in the difference case. But before we do that, we will just slightly modify our definition of these Fourier modes of the solution of the Mathieu equation. And so we assume that n is greater than 0, and we rescale the coefficients an in the following way. So we just put an equals to lambda, lambda to the power n times Cn. So we trade an for Cn, and the reason is that we can, in this way, isolate the dependence on lambda in just one term, right? Because here we have a lambda to the power n factor. Here we have lambda and lambda to n minus 1. So again, lambda to the n factor. And we have lambda squared times Cn plus 1. Right? So this is the first step, and the next step is that we divide by Cn minus 1 to get, so So let me just do it here. So Cn minus 1. So this becomes this becomes 1, and this becomes Cn over Cn minus 1, Cn plus 1 over Cn, right? So this is my Riccati equation if I denote these coefficients somehow. For example, let's call it alpha n. So then we have a first order nonlinear difference equation for alpha n. And now we can solve this equation in the following way. So we just write first Cn over Cn minus 1 as, so I'm just expressing it from this equation. It will be mu plus 2n squared minus e minus lambda squared times Cn plus 1 over Cn. Okay. And finally, this expression allows us to write the whole solution as an infinite fraction. So let me just expand this. So suppose I want this C1 over C0. So then this will be 1 over mu plus, I think my signs are wrong. Yeah, so probably minus here and plus here. Is that okay? Yeah, now it should be okay. So basically, I want to put this term on the other side. Right, and so then we have E minus mu plus 2 squared minus lambda squared. So here I have C2 over C1, but I continue to write it as 1 over E minus mu plus 4 squared minus lambda squared. And here I now have C3 over C2 and so on. 1 and so on. So we have this infinite fraction. And of course, we could do the same in the case n less than 0, in which case we would get something like C minus 1 over C0. So this was a 1 over lambda a naught, and this will be a minus 1 over lambda a naught. So this is going to be another infinite fraction of the very same kind, e minus nu minus 2 squared minus lambda squared 1 divided by e minus nu minus 4 squared minus lambda squared and so on. Okay. So we have these two expressions for this ratio and this ratio, and it remains to consider the equation with the difference equation with n equal to 0, which is nothing but this mu squared minus e times a naught plus lambda a minus 1 plus a1, which should be equal to 0. And so this equation will become an equation relating E and nu, right? Because if we, once again, if we, for example, erase, if we divide by a naught here, and substitute the continued fractions we had before, we get an equation of the following kind. So nu squared minus E plus lambda squared over E minus nu minus 2 squared minus lambda squared and so on, plus another infinite fraction of the same type, lambda squared here, E minus nu plus 4 squared plus and so on. So this should be 0. I think I'm again wrong with signs. So somehow, if I check my notes, so it should be plus here in front of the energy and minus here. Okay, so this is an equation relating monodromy parameter nu and accessory parameter E. And now we can solve perturbatively in lambda for the accessory parameter. So we look for E in the form E naught plus lambda squared E2 plus lambda to the fourth E4 plus and so on. So all you have to do in order to determine these coefficients is, well, substitute this ansatz into this continued fraction and truncate it at the desired order. So, for example, at the order 0, so what we get from here is just something like this: minus nu squared plus E naught equal to 0. Okay, so E naught is nu squared. At the order lambda squared, what we have to do is we have to keep the term E2 lambda squared coming from here, sorry. And then in these continued fractions, we can throw out all of these terms and replace the energy by the zeros order approximation. So we have plus lambda squared over nu squared minus nu minus 2 squared plus lambda squared over nu squared minus nu plus 2 squared. And this should be equal to 0. And this determines E2 for you. So here we get E naught equal to nu squared, E2 equal to 1 over 2 nu squared minus 1. And, well, it's a triviality to compute any desired order of this expansion using computer algebra. So this function E, which is a function of monodromy parameter nu and lambda, so this is what I will call accessory parameter function for Mathieu equation. And it is precisely this function here which will be later related to the quasi-classical conformal blocks. Okay. Yeah, and in the literature on special functions, this is usually called Mathieu characteristics. So to summarize, we have considered a specific second order linear ordinary differential equation, and we have solved the direct and inverse monodromy problem for it, at least in a certain sense. So the solution of the direct problem was given by this Hill's determinant here. And the solution of the inverse monodromy problem was given by the continued fraction. Right. So now I am going to switch to linear systems, but before, I don't know, maybe there are any questions on that.
Oleg, just maybe going ahead. Because I'm looking at this from the point of view of some spectral curve. So this probably corresponds to some spherical, right? Spherical spectral curve. Is my understanding correct?
I am not sure.
I would call this determinant as a spectral curve. So in the more standard point of view, this nu is a quasi-momentum, and it is function of E, and this determinant is indeed. And so if it were a general periodic potential, let's say finite gap periodic potential, then we would just arrive to the hyperelliptic curve in this determinant.
Perhaps if you can rephrase your question a bit, it would be easier to answer for me.
I also have a question. Oleg, so this near lambda equals 0, no? You have a singularity in the potential in the change of variables. So in the beginning, you were saying that you have this potential V.
Right, so I'm going to the potential. So the potential is here, yes?
Okay, so now you're solving, no, you're still solving in the variable. Okay, no, you're solving the variable X here. So yes, so no.
Yes, so lambda is a parameter.
Yeah, no, I was thinking in the variable Z. So in the variable Z, you will have a kind of essential singularity as Z equals 0.
An essential singularity of the solution, right, but not of the potential. So in the potential, you see, if we set here lambda equal to 0, so this is a regular singular point. But now the presence of these terms here, they mean that z equal to 0 and z equal to infinity, they are irregular singular points of this equation, but non-generic ones. So actually, I will come back to this a little later when I will discuss the connection with Painlevé equations.
Maybe I can try one more time to answer Leonid's question. So exactly for this slide, you look at nu. So nu, you can again kind of try to study Flaquet equation, considering them as eigenvalues, eigenfunctions of monodromy matrix. So you can consider monodromy as a kind of the transition of the solution over the period. You would get monodromy matrix, and nu is going to be just this monodromy matrix, of course, depends on lambda and e through the kind of canonical solution of equation. And this nu is going to be eigenvalue of this monodromy matrix. And monodromy matrix, so the characteristic equation for monodromy matrix, it is a spectral curve. Actually, it is this term appeared first exactly in this context when you study finite gap solutions, finite gap potentials. Then it is exactly where we first began to use term spectral curve in this context. So spectral curve, it is if I recast all these Oleg constructions, not as this discrete version of this, but using the monodromy matrix, 2 by 2 matrix, then it would be exactly the characteristic equation for this monodromy matrix would be spectral curve.
But just maybe it's a little premature nevertheless. So if we just consider this, well, Oleg or whatever, Hills or Mathieu construction, probably we also can get, so because it's also all related on asymptotic conditions on your variables, right? This convergence of this continued fraction expansion. So probably with different asymptotic conditions, for instance, we probably can make it, make different regimes, so we can obtain a more general equations for the zero level in the leading order, like getting some curves of higher genus or whatever. So just higher algebraic equations.
Well, perhaps I have understood a bit better your question. Please tell me if it's the case. So if I write this spectral curve here, so we have something like p squared plus v of z equal to 0, and this is equivalent to an elliptic curve. So this is already genus 1. It's not spherical.
I wanted to say yes, of course. In special choice of coordinate, you can write it like an elliptic curve, of course.
Well, so this is just the simplest Seiberg-Witten curve that you have. Okay. Any other questions?
Oleg, I will use this interruption. Just can you say something more, probably in future, about this relation with quasi-classics of conformal blocks and Mathieu?
Yes. This is what I'm going to explain. I don't know if I will have time to discuss this today, but essentially the statement is that so this accessory parameter function is well up to some redefinition of constants and parameters. So this is something like logarithmic derivative of the quasi-classical conformal block, quasi-classical Virasoro conformal block. So this is the so in the language of gauge theory, that would correspond to Nekrasov-Saakashvili superpotential. But let me just discuss this a little bit later. Okay. So the point here is that these functions that basically were introduced in like almost 2 centuries ago, which are already implemented in Mathematica. So they turn out to be related to rather modern studies on these conformal blocks and partition functions of supersymmetric gauge series. Okay, so let me now go to the second part. So now I switch to linear systems. So the statement that I want to explain is...
Sorry, Oleg, for interrupting you again, but does it have any relation with some Painlevé, this stuff, or not, not quite?
Yes, exactly. So actually we will have a triangle of relations. So we will have accessory parameter functions. We will have Painlevé functions. So there is a relation between this and this. So basically, accessory parameters, they are related to zeros of Painlevé tau functions or movable poles of solutions of standard Painlevé equations. And both of these functions, they are related to Virasoro conformal blocks. So this arrow corresponds to c equal to 1. This arrow corresponds to c equal to infinity. And now the question, so the point that I want to make and explain in the second lecture is that so this classical relation between Painlevé and accessory parameter story, it actually translates into identities between conformal blocks f infinity, so this quasi-classical conformal blocks, and c equal to 1. Now this c equal to 1 conformal blocks, as far as I understand from the previous lectures, so there are claims that well, this is something like partition function of the topological recursion. Yeah. And c equal to infinity conformal block, well, it's something like, well, if you want, this is a quantum period. Or inverted quantum period. But indeed, so we will turn back to those questions in the next part. Okay, so linear systems now. I will try to be very schematic here. So I want to show that solving Painlevé equations is equivalent to the solution of inverse monodromy problem for a linear system. And here I am careful about the choice of the word. So constructing the linear system with given monodromy instead of saying solving linear system with given monodromy. And to explain this subtlety, let me consider an example. The example is a Fuchsian system with 3 regular singular points. So let's say at 0, 1, and infinity. So here the matrices A0, A1 are 2 by 2 and traceless. So the fundamental matrix solution is a multivariate function on the Riemann sphere with 3 punctures, and we have 2 spaces which are associated to this problem. So the first space, let's call it A3. So this is the space of all linear systems. So this is the space of triples A0, A1, A infinity of matrices in, well, 2 by 2 traceless matrices, which satisfy one condition. So they should sum up to 0. And we have to consider them, of course, up to conjugation, because conjugation of those matrices leads to an equivalent system. So this is the first space, which is the space of equation data. The second space is the space of monodromy data. So here we have 3 monodromy matrices, M0, M1, and M infinity, which are in SL2C and which multiply up to identity. So the product is a 2 by 2 and identity matrix, and as before, so this has to be considered up to conjugation. Now, associating to each linear system its monodromy defines a certain map, right? Phi, which goes from A3 to M3. So this is called the Riemann Hilbert map or Riemann Hilbert correspondence. And well, a part of this map is easy to describe. Namely, if the spectrum of, if the eigenvalues of AK are given by, are denoted by plus minus theta k, then the spectrum, the eigenvalues of MK of monodromy matrices, they are also easy to write, 2 pi I theta k. And now, well, we can ask 2 questions. So as before for Mathieu. So question 1. So we could ask to find A's in terms of M's. And question 2, we could ask to solve for phi in terms of M's. So I want to distinguish these 2 problems because here we only want to reconstruct the linear system from its monodromy, and here we want to solve that linear system. Now the first question is considerably easier one because, well, I guess most of you know that so if we have a Fuchsian system in rank 2 with only 3 regular singular points, then it is rigid. So basically it means that the conjugacy class of monodromy is determined by only local properties, local monodromy exponents by these thetas. And the same holds for A's. So for example, I could write A infinity, I could choose a representative in the conjugacy class where A infinity is diagonal, and then my A0 would be given by something very simple, some rational function of thetas. So theta 1 squared minus theta 0 squared minus theta infinity squared, and some expressions here which I am not going to write. I just leave it as an exercise to students. So the point is that in order to find a parametrization of this matrices A, well, it suffices to know theta. And if you want similarly to describe the conjugacy class of M's, well, we have somewhat similar expressions, but instead of these rational functions, we will have some sines and cosines. So this is about question 1. Now for question 2, so if we want to solve for the fundamental matrix phi, then this is also possible to do, but the answer is rather complicated. So the answer will be expressed in terms of hypergeometric functions whose parameters will depend on these thetas. So this will be functions of Z. So what I want to stress is that the complexity of this problem has nothing to do with the complexity of this problem, of question 2. And in what follows, we are going to concentrate on question 1 when we will be talking about Painlevé equations. Okay, so how do these Painlevé equations arise? Well, it just comes out when we try to generalize this example. So the first generalization one can think of is to increase the rank. So let's put 3 by 3 matrices instead of 2 by 2. And then, unfortunately, this is a major open problem so I mean, even question 1 is an unsolved problem in this business. So we don't know how to explicitly express monodromy in terms, monodromy data in terms of equation data or vice versa. Another generalization which one can think of is, well, instead of increasing the rank of the system, well, let us just add here one extra Fuchsian singularity. So we add here AT divided by Z minus T. And now another exercise for students is to show that the dimension of this space of Fuchsian systems with 4 regular singularities and fixed monodromy exponents coincides with the dimension of the space of monodromy data and is equal to 2. So since both dimensions coincide, it means that for any value of parameter t, of the position of the 4th singularity, in principle, we should be able, so for any choice of monodromy, we should be able to find the corresponding Fuchsian system. And this now allows to do isomonodromic deformation. Because if we now vary the parameter t and require the monodromy of our Fuchsian system to be the same, then it is a very well-known classical fact that the residues satisfy the system of Schlesinger equation. So we have the derivative of A naught is this, the derivative of A1 is a similar expression, AT A1 over T minus 1, and A naught plus AT plus A1 is equal to minus a diagonal matrix, so just a constant. So these are isomonodromy equations, and well, this is equivalent to Painlevé 6. But the point I want to make here is that if we somehow find for any given monodromy the Fuchsian system which is characterized by this monodromy, then we get this Painlevé 6 equation or this differential equation as a bonus. So these equations are automatically satisfied by equations are automatically satisfied by the solution of the inverse monodromy problem. Okay, and so instead of solving this differential equation, we are going to attack instead this problem here. So we are going to try to reconstruct a linear Fuchsian system from its monodromy. Now it seems that I have already spoke for an hour, so it went much slower than I expected. So perhaps perhaps there are some questions here, and also please tell me, should I stop or should I continue? What should we do now?
Sash, you are in charge.
Oh, why I think Vladimir introduced.
Because you started.
Huh? Vladimir introduced.
No, I mean, I think that it's time, at least it's 1 hour, and I think it's a good point to stop here. If, of course, people should ask questions if they have, and but I think that it is a good point to stop today.
Mm-hmm.
Yes, I agree. So Oleg, I actually have a well, I don't know, naive, not naive question.
Okay, maybe we can thank
yes
before we start questions. Thank you, Oleg, for your talk.
Yes, thank you.
And I will stop recording for the question section.
Okay. Yeah.